Hello students, here's lesson 10, discussion of satellite ocean study. Turns out that satellites can study Earth from space using a variety of sensors. These inform us about ocean temperature, circulation, biology, and surface elevation. Described here, some of the more important satellites used for studying the ocean. A very important set of satellites, first TOPEX and now JASON from 1992 to the present. Very successful series was designed to provide a snapshot view of ocean circulation. Here's how it works. TOPEX and now JASON orbit Earth every 10 days. As they do so, they precisely measure changes in the elevation of the ocean surface. They do this with radar, very precise. Warmer water inflates, so it rises upward just a few inches in elevation. Colder water condenses, and that would have the effect of lowering ocean surface elevation. So JASON provides us with updated maps of ocean circulation based on surface elevation, and that's related to temperature. So here's a map showing ocean elevation temperature from our JASON satellite data. So it's a snapshot from December 20th, 2013. The redder areas are where it's warmest, and the blue to violet, that's where it's coldest. And that distribution is just about what we would expect, with the warmer water in the tropics and the colder water toward the poles. If you look at these maps in sequence over a period of weeks or months, then the circulation of the ocean becomes fairly evident. JASON and TOPEX initially provides us with an early warning of the beginning of something called El Nino. El Nino is actually a very warm ocean current, travels clear across the Pacific Ocean, easily identified by JASON. The warm water, the El Nino, temporarily disrupts marine life, and in so doing it can also generate heavy rainfall in normally dry regions on land. This occurs in South America as well as in North America, Southern California, for example. So the El Nino of 1997-1998 was the last major El Nino event, and it shows here, and this is from Jet Propulsion Laboratory, the white on the globes are where the water is warm. These are elevated water masses. Let's go to that same view, but we'll enlarge it some. So look first at the version that's considered to be normal. That's February of 1999, a fairly normal view of the Pacific Ocean, with the violet in the center representing very cold water. And then off to its left, or to the west, we have the red and then the white representing very warm water. That's typical temperature distribution within the Pacific Ocean. And if you find the coast of South America, way off to the right-hand side in the black, that's the west coast of South America with Peru and then up toward Colombia, and then go up along the coast of Mexico and up toward Southern California, you can see the water temperatures fairly cool. If you go to November of 1997, the max of the last El Nino event, look at the distribution of water temperature here. You can see all that warm water, white and red, is now hugging the coast of South America, Central America, and Western North America as well. So our water temperatures had raised anywhere from 10 to 20 degrees Fahrenheit during this El Nino event. So JASON, and formerly TOPEX, they inform us about this. They allow us to see it coming and to provide an advance warning for people who need to know about such events, people that plan for disasters, for example. They need to know. So another satellite of significance is called GEOSAT, a military satellite that was in orbit from 1985 to 1990. GEOSAT also used radar to make very precise measurements of permanent irregularities in surface ocean elevation, not those transient changes that TOPEX and JASON measure. So elevated portions of the ocean can exist due to underwater mountains. They have a great mass and therefore greater gravity than the ocean floor around them. This draws water toward those underwater mountains. We call them seamounts. This image illustrates that. You can see the ocean floor, and you've got that volcano on the ocean floor, and you can see the water above it is higher in elevation. So GEOSAT was able to map that out with great precision. back in the later 1900s. Eventually, the military released this GeoSat data to oceanographers in the early 1990s, and from that data, they were able to develop very detailed physical maps of the ocean floor. This is for the entire planet. Up until then, we had pretty decent maps, but nothing as detailed as what GeoSat provided us. So here's a very nicely rendered map showing details of the ocean floor, complements of GeoSat. And we'll take a little closer view, Eastern Pacific Ocean. So you can now see those details. The main feature going vertically in the middle of the image, that's the East Pacific Rise. It's a divergent plate boundary. It's essentially an underwater mountain chain. We knew it was there, but we just didn't know the dimensions. You can see those linear features branching out in both directions from the East Pacific Rise. Those are fracture zones. And then all the little bumps on the ocean floor, those are underwater mountains, those seamounts. So GeoSat was able to provide oceanographers with these very detailed views of the ocean floor, and that's why we now have wonderful maps of the entire ocean floor, complements of GeoSat. Other satellites, SAR, SST, provide details about the ocean surface. So we'll take a quick look at each one of these. SAR, synthetic aperture radar data, uses radar signals sent from satellite to ocean surface. And what it's going to do is identify very small scale surface ocean disturbances. It has an onboard altimeter to measure elevation above the ocean. And then the travel time for that radar signal to the ocean and then back to the satellite can be calculated. And that gives us very good details about wave size and in general the roughness of the ocean surface. Therefore, features such as circular flowing ocean eddies, pictured here, which can entrain oil, can be identified. Whenever they entrain oil, and this can be natural oil released from the ocean bottom, it actually flattens out the ocean surface. So the lighter shades of gray here, that's rougher water. And the darker shades is where there's oil that's actually flattened the waves. So using SAR images, you can get a real detailed view of circulation of the surface ocean. And if you want some geographical reference, we have Point Conception up to the top left, Santa Cruz Island down to the right middle, and there's an eddy in the very center there, and you can see some of the circulation highlighted by the oil entrained in the eddy, which helps to flatten and therefore define the eddy. The SST, sea surface temperature, can be identified by satellites that carry radiometers. These are very sensitive. They can measure the radiation of heat from the ocean. NOAA has polar orbiting satellites, and they've been using this technology since 1978 to inform us about the surface ocean temperature. So here's a view of an SST image showing the same eddy as what we looked at with the SAR image. So the blue here is cold water, red is warm, and as you look at this, you can tell you don't quite have the details, the resolution of the SAR data, but it's a good tool to pick out water temperature and then relate it to circulation of the ocean. And the next slide, it's a comparison. SAR is on the left, SST on the right, and you can see they're looking at the same exact eddy. You can see Santa Cruz Island and some of the other Channel Islands, as well as Point Conception. So each one provides data from very different types of sensors on satellites. So this was just to inform you about how satellites can be used to study the ocean and some of the details they give us about the ocean.